This video demonstrates our vector field system. First, we show how a user can create a planar vector field. The user creates a vector field by using regular elements. Each regular element is extended to a global basis vector field with the same direction but decreasing magnitude away from the center. This allows several basis vector fields to be summed. Notice, unintended singularities may appear, such as the saddle shown here. The user can also create a vector field by using singular elements. Here, the user puts down two center elements with opposing directions to form a dipole. When the user adds a source element, a saddle appears. This is due to the topological constraint known as the Poincaré-Hopf theorem. The user can perform topological editing operations to handle these singularities. The system can also be used to create vector fields based on analytical properties such as curl and divergence. First, the user creates a curl-free vector field by using only isotropic source and sink elements. Typically, the separatrices divide the domain into quadrilaterals, as shown here. Within each quadrilateral, all the trajectories start at the same source and end at the same sink. Next, the user creates a divergence-free vector field by using only isotropic center elements. Generally, the separatrices divide the domain into regions, inside which there is a family of periodic orbits circling a common center. Our system can be used to create generic vector fields that are neither curl-free nor divergence-free. Now that the initial vector field is created, our system provides editing operations such as flow rotations and reflections. Here, the initial vector field is rotated globally. Notice flow rotations do not alter the number, location, or Poincaré index of the singularities. However, a source may become a center, as shown here. A saddle remains a saddle, but the incoming and outgoing directions are rotated. Now we will rotate a vector field back to its original form. Pay attention to the directions of the saddles. Flow reflections negate the sign of the Poincaré indices. Here, a saddle becomes a center. Performing reflection a second time brings the vector field back to its original state. Flow smoothing is used to reduce vector field complexity. Here, the user first specifies a region as bounded by the white loop. The system then performs a vector-valued smoothing operation on the vector field inside the region. Notice the vector field topology is also simplified. Here we compare the original field with the simplified version. The user can also perform topological editing operations directly. In this example, the user performs cancellation on a source and saddle pair. Notice how the flow is locally changed after the cancellation. The system is capable of canceling a saddle and center pair automatically, as shown here. In this instance, this process is demonstrated manually by the user. First, the vector field is rotated by -90 degrees to change the center to a source. After the cancellation, the vector field is rotated back to the original configuration. Singularities can also be moved with our system. Here, we show an example of moving a source. Notice how the local flow is deformed. Due to numerical difficulties, moving a saddle is considerably more challenging. Our system achieves this automatically by using a flow reflection to change the saddle to a source. Here again, we demonstrate this process manually. In addition, limit cycles can be created utilizing our system. In this example, the user first creates a source surrounded by 4 sinks and 4 saddles. Then, the user performs sink-saddle cancellation in a consistent direction. This creates a limit cycle that separates the flow from inside to the outside. Here are some examples of applying our design system to painterly rendering. The first example image is a human eye. The user puts a center element in the middle of the eye. Next, they place a saddle element at the corner of the eye and adjust the orientation of the saddle. Finally, the user emphasizes other main features in the image by using regular elements on the lower eyelid and eyebrow. Once the user is satisfied with the results, the resulting vector field is exported to an offline, high-quality renderer. This Van Gogh-style image was created using the exported vector field with the renderer of Hayes and Issa. In this accelerated example, the user creates a vector field to match the features in a cat's face. This is the impressionistic render, again based on the Hayes and Issa algorithm. We will now demonstrate our system for vector field design on 3D surfaces. To begin, the user puts a source on the bunny's head. Notice unwanted singularities appear at faraway regions near the tail. To solve this problem, the user then puts a sink element in the middle of the tail. This produces a vector field that is natural to the main features of the bunny. Notice the sinks at the tips of the ears and the saddles at the roots. Our representation supports topological analysis of vector fields on surfaces. In the second example, the user creates a vector field on the surface of the bunny with regular elements. First, the user adds a regular element on the shoulder of the bunny. Again, this creates several unwanted singularities on the opposite side. By adding another regular element, most of these singularities are eliminated. However, several remain around the bunny's head. The user chooses to perform a singularity pair cancellation, in which a source and saddle pair is removed. This process is similar to the method used in the planar case, which is based on the Conley index theory. Also, a source is moved. In the next example, we demonstrate flow rotations on surfaces. First, the user creates a vector field with a pair of source and sink elements. Then, the user applies a series of flow rotations to the vector field. In particular, the vector field produced with a 60-degree rotation is used for texture synthesis. Notice the pair of singularities is clearly visible in the synthesis result. Let us compare the synthesis results on the front of the bunny with two vector fields. Notice the vector field shown on the left has many singularities in the front, and they cause the breakup of the synthesis pattern. The vector field shown on the right has few singularities in the same region. In this case, the user puts a tiger stripe on the feline based on two different vector fields. Notice the underlying vector fields are clearly visible in the synthesis results. We have also applied vector field design to non-photorealistic illustrations on surfaces. With the dragon, notice the underlying vector fields result in different visual effects.